Okay, in this installment, we're going to continue to do examples of acid and base equilibria, um, dealing with small values of the equilibrium constant, either Ka or Kb. And we're going to look at the effect of salts of common ions on the pH and the solution composition. Let's consider a solution of 0.030 molar hydrozoic acid. Ka for hydrozoic acid is 2.2 times 10 to the minus 5. And so we can set up our ice table like this. Right? So now we can see, right, we've got this set up here. Right? I've got the equilibrium, hydrozoic acid dissociating to form hydrogen ions in the water and azide ions in the water, right? Our initial concentration of hydrogen ion and azide ion is 0. If X of our acid dissociates, we get X hydrogen ions and X azide ions, right? We get 0.03 minus X, X, and X. But since our Ka is small, we are going to try first to see if we can save ourselves some time, right? Saying that is close enough to 0 that it won't affect our calculation, or at least not enough to matter. And so we end up with our Ka, 2.2 times 10 to the minus 5 is equal to X times X divided by 0.03. When you multiply that out, you get 6.6 times 10 to the minus 7 is equal to X squared, right? Multiply through by 0.3. And so then you get 8.124 times 10 to the minus 4 is equal to X, right? 8.124 times 10 to the minus 4 divided by the 0.03 we ignored it relative to is equal to 0.027, right? That is less than 0.05. So our assumption works for this case. So we can use that number. And so the pH, right? The pH is equal to the negative of the log of 8.124 times 10 to the negative 4. It's a bad 4, right? And that is going to be equal to 3.09 as our pH, right? And we know that there's an estimate here, right? But we're willing to accept that small amount of error in this problem to save ourselves a lot of mathematical work, okay? So that's reminding us what we did last time. Now let's make a small change for the next one. So now let's consider a similar problem. We've got, right, the same concentration, 0.030 molar hydrozoic acid, but we've also got 0.01 molar sodium azide in the reaction mixture, right? And if we think about this, our equilibrium from the previous problem will be affected by the presence of azide ion, right? A product which should push our reaction back. So what is going to be the new equilibrium position? Well, if we remember our instructions, right? Right, come back here, right? So first we consider complete processes. And dissociation of this soluble sodium salt will be our complete process. So if we take our sodium azide, it will completely dissociate to form sodium ions in the water and azide ions in the water, right? If our initial concentration And if we made up our solution as 0.01, the change, because it's complete, is that all of our reactant will react. So we know what that is, and we know what that is. And so when we reach our final, there's none of our reactant left. All of it is either sodium ion or azide ion, right? And so after we've done a number of these, you'll start to get a feeling for that whatever, if it dissociates 1-to-1, whatever the concentration of our initial salt is, that's going to be the concentration of the ion that we're looking for, right? And so you'll get to the point where you don't have to do this table. But now we've considered our complete process, and so now we have to consider our equilibrium process. Right? We go complete first, then equilibrium. And our equilibrium process is our dissociation of our hydrozidic acid. Right? And if we set up our table, if we look at our initial conditions and our change, and in this, almost let me get away with one, right? This one is an equilibrium process, and we should write it that way to remind ourselves, right? Don't get in too big a hurry, right? So our initial concentration of our hydrozidic acid is given in the problem, right? Our initial concentration of hydrogen ions, we haven't considered making any in our problem yet, so it's 0 at the moment. But our concentration of azide ions, since we already have this going on, is going to come from here, and it's going to be 0.01, right? Now we consider our changes, minus x plus x plus x, and we're going to get 0.03 minus x, we're going to get x, and we're going to get 0.01 plus x. And so that becomes the starting point for us to do the math for our equilibrium process. So if we just keep, the part for the equilibrium process now, right? Now we've got, right, these expressions. But if we look here, right, we have a small value of Ka, which before meant we could ignore this x relative to 0.03. Well, if x is small relative to 0.03, it might be small relative to 0.01. So our first attempt should be to, right, assume x is close enough to 0 to count on both of those terms, right? So when we write out our Ka expression, right, so our 2.2 times 10 to the minus 5 is going to be equal to x times 0.01 divided by 0.03, right? And so when we do that, we're going to get that 6.6 times 10 to the minus 5 is equal to x, right? Let's see. So 6.6 times 10 to the minus 5 divided by, let's go the smaller one, 0.01 equals 6.6 times 10 to the minus 3, right? Which is less than 0.05, our 5% limit to accept our estimate. And so 6.6 times 10 to the minus 5 as x works. We go back to how we defined that. That is equal to the equilibrium concentration of hydrogen ions, right? And so now we can find that the pH is equal to 4.18. And if we wanted to, we could find that the hydroxide ion concentration, right, that the concentration of hydroxide ions is going to be equal to our Kw divided by our concentration of hydrogen ions, right? 1.0 times 10 to the minus 14 divided by 6.6 times 10 to the minus 5, and you get the concentration of hydrogen ions as being about 1.52 rounded times 10 to the minus 10 molar, right? You always have to remember that when we're doing these equilibrium problems, we have to work them in molar concentrations, and our answers will come back in molar concentrations. Now, if we look closer at this problem and sort of pare away some of our extra stuff, right, remember it came down to, right, this equation after we'd made our assumption, right? And if you look at this, right, we got this number here, and we got this number here, right? So really what this equation came down to was that our Ka was equal to our concentration of hydrogen ions times the concentration of the basic form of our acid divided by the concentration of the acidic form, right? If we knew those two, right, this ratio was what was important in determining the hydrogen ion concentration, right? So now we've got something we can generalize to make a lot of these problems easier. If we know what the concentration of our basic form is after dissociation, and we know what the concentration of our acidic form is, we can just put this in here. If we know the Ka, we can find the hydrogen ion concentration. It becomes a very straightforward way to find the hydrogen ion concentration, okay? Right? So now let's just look at a slight variation of this problem, right? Let's just change the concentration of the sodium azide to 0.060 molar, right? We should be able to work it fairly straightforwardly, right? Again, we start with our complete process, right? You always start with complete processes first, and in this case, that's going to be the dissociation of the soluble sodium azide, right? And so you've got sodium azide going to sodium ions and azide ions, right? From what we saw in the last problem, right, in a dissociation like this, if we start out with 0.060 molar of that salt, then at the end we're going to end up with 0.060 molar of the product ion. And so then we can consider our equilibrium. Right? And if our equilibrium is hydrozoic acid in equilibrium with hydrogen ions and azide ions, right? Then, right, our initial state is the 0.030 given in the problem. Here it's 0.060 that we found from our complete process, right? The products of the complete process can influence our equilibrium, right? 0 of that. Our change is going to be minus x, plus x, plus x. When we reach equilibrium, we'll have 0.030 minus x. We're going to have x. We're going to have 0.060 plus x. Right? We still have our small equilibrium constant, so we're going to make our assumption here and here, right? That adding a very small number won't change that. And so we're going to get, as our problem, 2.2 times 10 to the minus 5 is going to be equal to x times 0.060 divided by 0.030. And running out of space here, x will be 1.1 times 10 to the minus 5. And then we can find, right, we can find the pH, and we can find the concentration of hydroxide ion, all from that. Okay? So it makes working the problem easier if you realize that with small values of the equilibrium constant, right, that x will not have a large effect here or here, and it simplifies our calculations if we discount that, right, ignore that small change, focus on the large amount that's there, make our problem easier to work. Now let's consider an important special case of these kinds of problems. So here we've got 0.030 molar hydrozoic acid, and here we've got 0.03 molar sodium azide, right? This becomes our initial concentration on the acid side. This dissociates, right? So we've already considered our complete process to make 0.03 molar azide ion, right? We start off with no hydrogen ion, minus x plus x plus x, and then we've got our situation again where, because our equilibrium constant is small, we can ignore, right? We assume that that is close enough to 0 to ignore it, and so we can work our problem in a straightforward way, right? Our Ka was 2.2 times 10 to the minus 5, yep, right? And so that's going to be equal to x times 0.03 divided by 0.03, right? That divided by that is 1, and we just get x. So we get that x is equal to our Ka, right? So this is why this is an important special case. If the concentration of the acid and its conjugate base salt are the same, then the hydrogen ion concentration, right? X was the final hydrogen ion concentration, is the Ka, right? Or if we found it, right, we can find that the pH is equal to the pKa, right? The negative log of the Ka. So that is a special case. If the amount of acid and its basic form are in solution together at equal concentrations, then the concentration of hydrogen ion is equal to the Ka, where the pH is equal to the pKa. Okay? That is an important special case we have to remember. Okay, so let's look at another kind of problem here, right? So here we have a solution of lactic acid, right? We're going to make it, 0.4 molar, but we're going to use something else, right? We'll put a pH meter in and we'll add a little sodium hydroxide or a little hydrochloric acid, whichever is appropriate, to get the pH to be 3.54. And so the question is, at that pH, how much of the lactic acid is still undissociated and how much is dissociated to form lactate ion, right? Right? Ic would become 8 lactate ion. And the Ka for lactic acid is 8.3 times 10 to the minus 4, right? So in this case, what we know is the concentration of hydrogen ions, right? Our concentration of hydrogen ions is equal to 10 to the minus 3.54, which is equal to 2.884 times 10 to the minus 4 molar, right? And so now if we look at our Ka expression, right, for our dissociation, right, I'm going to abbreviate lactate that way, right, going to hydrogen ions in solution and lactate ions in solution, right? We could write our Ka expression is going to be equal to the concentration of hydrogen ions times the concentration of lactate ions divided by the concentration of undissociated lactic acid. But we know two of those numbers, right? So we get, right, our 8.3 times 10 to the minus 4 is equal to our concentration of hydrogen ions, which is 2.884 times 10 to the minus 4 times the concentration of lactate ion, all divided by the concentration of lactic acid. And if we divide both sides by this number, right, we get that 8.3 times 10 to the minus 4 divided by 2.884 times 10 to the minus 4 equals 2.878, right? And so we know that that is equal to the concentration of lactate ion divided by the concentration of undissociated lactic acid, right? The ratio of those two numbers is 2.878, right? Here we are with the essential information carried over, right? Our problem is, right, that's a fine equation, right? We got a number, but we had two things we don't know, and we can't solve an equation with, one equation with two unknowns. We need something else that relates these two unknowns in order to solve. If we can solve for one, we can solve for the other. But what we can go back to here is, right, that everything at the start was lactic acid, and all of the lactate and lactic acid at the end started as part of that, right? And so we can use that relationship that, right, our 0.40 molar that we have now is going to be equal to the concentration of lactate plus the concentration of lactic acid. Now we have two equations and two unknowns that we can solve, right? If we go back up to here and multiply through, we can get that the concentrate, that 2.878 times the concentration of lactic acid is equal to the concentration of lactate. We can substitute this number in there, and so you get 0.40 equals 2.878 times the concentration of lactic acid plus 1 times the concentration of lactic acid, right, equals 3.878 times the concentration of lactic acid, right? And so 0.40 divided by 3.878 would be the concentration of lactic acid, right? Which would equal 0.103 is the concentration of lactic acid. We can substitute that back in here and solve for concentration of lactate. So there are a lot of variations of these problems. All of them you have to keep track of. Are there any complete processes that happen first? Then deal with equilibrium processes. And what's really important is the ratio of the basic form to the acidic form in determining the final equilibrium.